So in 731, it says, assume that the interest is added at the beginning of the new year. Make one graph that shows how each type of investment, simple and compound, starts with $1,000 and grows over 8 years. Discuss the following questions with your team as you graph. So it says that we should consider, like, how are we graphing in terms of color? Is there a way to make this easier that way? We also have to think about what happens with the money between the years. So, like, in the middle of a year, what's going on? And how can I represent that between amount on a graph? So as I start to think about my equations, the first thing that comes to mind is, oh, well, the first one is a linear equation, because I'm just adding $80 each time, and I start off with $1,000. The compound equation looks a little different because that's got that exponential going on, where it would be 1,000 times 1.08 to the x power. And then I think about my graph and I make the points on a table just because it makes it a little bit easier. And as I think about those equations, I'm going to add them in. So y equals 80x plus 1,000 and y equals 1,000 times 1.08 to the x power. So that's kind of what I've got going on here. Let's make that a little thinner so it's a little easier to see what's going on. Okay. However, they bring up a good point. What's happening between the years? Because based on my graph, this shows me that at 0.5 of a year, so like on June 1st, halfway through the year, that I should have $1,040 in the account. However, like they said, the money only gets added at the beginning of a new year. So really what should be happening is I should see something that looks more like this. Now I have to figure out, how am I going to address that? Because that's not quite what I'm seeing on my graph. Okay. And then if I think about year one, same thing would happen. I don't actually have $1,100 at some point in the account. I go straight from $1,080 to $1,160 or $1,166.40. So it looks more like that. And then year 2 to 3, like that. Year 3 to 4, like that. So I need a way to make that more clear in my equations, because this model, while it's somewhat helpful for us, it's not actually accurate for the rest of the time. Now, these graphs have a really interesting name. They're actually called step graphs, functionally because they look like steps. So we're going to think about both our equations that help us figure this out, but also like what that step function situation looks like to help us through 32. So it says, thinking about the growth and starting point for a simple and compound interest equations or interest situations from this lesson, model each of the two step functions with an equation. Let y represent the money in the account after x years. So we've got our equations here. It's a little bit hard for us to figure out how to make it do that thing where it's going to like go like this. But we do have our equations for the moment. Let's skip on down to part C. It says, use your model to predict how much your original $1,000 investment would be worth at the end of 20 years in the credit union. So what they're telling us to do is plug in 20 for X in each of these two places. Now keep in mind, they're saying the end of the year, but that doesn't actually matter because, like we said, it's flat all the way through the year. So it doesn't matter if I'm checking the amount of money on January 1st or December 31st, the same amount is in the account the entire time. So I'm going to plug in 20 for X in my first equation. So 80 times 20 plus 1,000. So in my first equation, that would give me $2,600 for doing 80 times 20 plus 1,000. For my second equation, I would do 1,000 times 1.08, and then I want to the 20th power. Now, in case you forgot how to get that, you're looking for the key that does exponents. So on my calculator, it's like this little caret looking key, but you might also have a key where it says like x to the y power. So 1,000 times 1.08 to the 20th power. On this side, I get $4,660.96. Notice the crazy difference in the amount of money you have when we're talking about compound interest versus simple interest. Again, it's just because this account is taking or giving you interest based on the other money that's in the account that you didn't actually put in there, the interest that you got. Now, Part D really gets at what we're talking about. So the reason that these equations are called a model instead of representation of the real behavior is because, like we said, this is what's actually going on, but that's really hard for us to create an equation to model. So these are 100% accurate on January 1. We just can't use any decimals in there. That's all they're trying to get at for Part D here is, could we write a model that something that models that step function behavior? Absolutely. It's just a little bit more challenging and frankly not super useful as long as we recognize that whatever I get for 2 is also true technically for 2.7, even though my model equation, these, might give me a different answer. Now, as we move forward in the course, we're going to use continuous functions to model situations unless we talk about otherwise. So we're going to use models like this, but step functions do exist, and it is possible for us to do that. That's just all we're trying to get at here with 32. Now, we have a third option for investing our account. It says a third option for investing money is a money market account, which offers 8% annual interest compounded quarterly, meaning 4 times a year. That means that our original 8% investment, so like up here it said 1.08, is divided into 4 parts over the year. So the bank pays 2% interest every 3 months. So in order to create a model for our value, what we would need to do is we're going to start with the same amount of money because we're doing the exact same thing. But this time, instead of having 8% and 20 years, we actually only have 2%, and we're just doing it 4 times a year. So we would say 4 times the number of years. Now, since they actually want me to write this in quarters, we don't actually need the 4. So sorry about that. It says use the model to find the value of your investment after 4 years. Now keep in mind, this is talking quarters. So in order to get the number of years, it would actually be 16 total quarters. So I would need to go y equals 1,000 times 1.02 to the 16. Okay, so in my calculator, 1,000 times 1.02 to the 16 power, which gives me $1,372.79. Now, if we go back and compare with what we had in our other models, so in our simple interest, after 4 years, we had $1,320, and in our compound interest, we had $1,360. And here we have $1,372. I wonder why it's higher. That's going to be part of what we kind of move through and talk a little bit about as we move forward. So the big ideas that we need you to walk out with today is in our equation, y equals a times b to the x. A is your initial value, or your y-intercept. B is going to be your multiplier. Other than that, if you are able to get a handle on how this equation is set up and how it's so similar to what we did when we were dealing with our sequences, you're going to be in a really good spot moving forward.